In this video, we're discussing finding extrema again, but now we've got another method for finding extrema called the second derivative test. The second derivative test is intimately related to this idea of concavity. We're going to define concavity in just a minute. The problem statements will generally ask you to determine the intervals where the graph of f is concave upward or concave downward. I'll show you how to do that. We'll discuss what's called a point of inflection. We'll define those, and then we'll define the second derivative test and use the second derivative test to find some extrema, determine whether we have relative mins or relative maxes. But first, concavity. We say the following is true. We say that the graph of f is concave upward when the first derivative, that's the slope of the graph, is increasing. So when f prime is increasing, we say that the graph is concave upward. Now we just talked about increasing and decreasing in the last couple of videos. We said that f is increasing when its derivative is positive and f is decreasing when its derivative is negative. So if f prime is increasing, what we're really saying is that f double prime, it's the slope of the slopes, it's the derivative of this one, that derivative of this one is positive. So f prime is increasing, that means the graph is concave upward, and that also means that f double prime is positive on that interval. And we're usually talking about an interval I. So we'll say that this is concave upward on an interval I when the first derivative is increasing on the interval I, and all of this is true. Now generally I'm looking at a graph and I look at it and I can tell it's concave upward because of the shape. If the graph looks like this, the graph is concave upward. And you're saying, that as opposed to what? Well, I'll show you concave downward in a minute. But this is concave upward. It looks like a cup facing up. Notice that at the bottom we have a slope of 0. And the slopes on this side, if we draw tangent lines there, I'm going to use my pink sticky note as a straight edge again. So the edge of this pink sticky note is serving the purpose of, it's playing the role of my tangent line. See how the tangent line is sloping down as I look at it from left to right? That slope is negative. Over here, it's even more negative. It's just steeper, right? And when we're close to the bottom, it's less steep, but as you look at it from left to right, it's still negative. It's still sloping down. All those are sloping down. So on this side, the derivatives are all negative, and it goes from being very negative, very steep, to less steep and less steep and less steep and less steep. And again, when you think about steepness, you want to think about like going to Turkey Mountain or going hiking or something like that. Is that like a hill that you would want to climb? I don't want to go down a hill that looks like that. That's very, very steep. That's not so bad. Maybe it's not challenging enough. But you get the idea. That is a very large negative slope. Like maybe that slope is like, that's a fraction. You know, that's a small negative slope. Maybe it's like -1/5 or -1/3, something like that. But we've got very large negative slopes and smaller and smaller and smaller negative slopes until we get to the bottom. Slope is 0 at the bottom. Then on the other side, what do you notice about all the tangent lines over here? That's a positive slope. That's a positive slope. That's a positive slope. All these slopes are positive, and the farther you get away from the bottom, the steeper they become. So over here, the slopes are positive, but they're getting more and more positive. So the slopes are going from negative to 0 to positive. What does that mean? The slopes are increasing. Because they're going from a very large negative number to a less large negative number, then eventually they get to 0, and then the slopes are increasing over here, and then they keep going and growing and growing, so getting steeper and steeper. If the graph looks like this, f prime is increasing, and if f prime is increasing, that means f double prime is positive, and the graph is concave upward. That's what it means for a graph to be concave upward. It looks like this, because the slopes are increasing. On the other hand, we could have concave downward. Slopes are decreasing. We say the graph of f is concave downward on an interval I when the first derivative is decreasing. And if the first derivative is decreasing, that's equivalent to saying that f double prime is negative. And both of those tell us that the graph is concave downward, the graph of f. If you look at the graph of f, f prime, and f double prime, they're going to have a relationship. We'll look at that later. But the graph of the original function, if f double prime is negative, the graph of the original function is concave downward. And what that looks like is sort of the opposite of this. The graph is concave downward. It looks like a cup facing down. At the top, the slope is 0. Over here, all the slopes are positive. And they initially start off very large and positive. We've got some very steep slopes. But then as we get closer to 0, that tangent line starts to flatten out. As we get closer to that top part, it's just less steep. It's still positive, but it's less steep. And then at the very top, the slope is 0. Then on the other side, it's not as steep, but the slope starts to be negative. And then it gets more negative, and then it gets to be more negative. And then eventually you're over here, and you've got a very, very large in magnitude, but negative number for the slope on this side. So f prime is negative on that side. So f prime is going from positive to 0 to negative. Well, that means that f prime is decreasing as you go from left to right. And if f prime is decreasing, that means the second derivative is negative. So graphically, that's what's going on. If I see a graph that looks like this, and I see a graph that looks like this one's concave upward, this one's concave downward. Now most graphs are not concave upward all the time or concave downward all the time. Most graphs have intervals where they're concave upward and intervals where they're concave downward. So maybe you have something that looks like this. This one's a little bit tricky too because of the curve I put on that at the end. See how this is concave upward for a while and then somewhere in between it switches? Because I don't have a formula for this, it's hard to tell you where it switches, but there's some place in here, maybe it's there. That location, I'll call it x equals c, y equals f of c, that's called a point of inflection. A point of inflection is just a point on the graph where the graph goes from concave upward to concave downward or vice versa. It has to be a point on the graph. So it goes from concave upward to concave downward, or vice versa. The other way around is fine. The concavity just changes. Vice versa, I think that's a C. There we go. So that's a point of inflection. So it's concave upward over here, concave downward over here, and then there's some transition point. You can see it's starting to curve up again. So there's going to be another point of inflection, maybe somewhere around here, because it's concave down, and then at some point it starts curving up again. Maybe it's actually higher. Maybe that's my second point of inflection. So you have concave upward, concave downward, concave upward. Let me mark up my graph. Now, I don't know what that x value is, and I don't know what that x value is, but maybe that's 3, and let's say that that's 7. Obviously, this is not to scale. So this is concave upward over here. So if someone said, where is this graph concave upward? I might say, just guessing for where those points of inflection are, that the graph is concave upward on the interval. We're always looking for intervals of x values from -infinity to 3. And it's also concave upward over here, starting at 7 and going to infinity. Okay, so it's concave upward there. Concave upward here. And then in the middle, it's concave downward. So from 3 to 7, it's concave downward. Okay, now if I don't have a graph, and actually if I want to be more precise than I even have been with this graph, the better way to show that a function is going from concave, or a function's graph is going from concave upward to concave downward, or vice versa, is to actually look at the signs of f double prime, because f double prime is positive where the graph is concave upward, f double prime is negative where the graph is concave downward, and that point where it transitions from concave upward to concave downward or vice versa, those are points of inflection. Now, if f double prime is 0, that does not necessarily mean you have a point of inflection, but the potential points of inflection are the x values where f double prime is 0. So at every point of inflection, f double prime is 0. 0 over there, and then, or it's positive over here, then the second derivative is 0 there, and where it's concave down, the second derivative is negative. So the second derivative goes from positive to 0 to negative, and then the second derivative will be 0 again, and then it'll go back to positive over here. Okay, so concave downward looks like a cup facing down, and concave upward looks like a cup facing up. Now, you're going to be asked in your homework to determine the intervals on which the graph is concave upward or concave downward. It's actually very similar to what we do when we determine the intervals when the function, where the original function is increasing or decreasing, except instead of looking at the intervals for the first derivative, we're going to be examining the intervals for the second derivative to determine concavity. And then points of inflection are where the concavity changes from positive to negative or negative to positive. Now that we know this, rather than finding or classifying relative extrema using the first derivative test, we have another option. We have what's called the second derivative test. And I think the second derivative test, I think it's a great test. It makes intuitive sense. You don't need to use it. You can always use the first derivative test. But when you get to calculus 3, there is no higher dimensional analog of the first derivative test. There is a higher dimensional analog of the second derivative test. So I think it's really important that you learn it here, not just because it extends in calculus 3, but because it's telling you something about what the graph looks like. Okay, so you're trying to classify some extrema. You get some critical points. And so let's say C is a critical point of F. I'll say let C be a critical point of F. That means that f prime of C is 0 or f prime of C is undefined. It's one of those. If the second derivative at x equals C is positive, then f of C is a relative max or min, one of those. So second derivative is positive, and the first derivative is 0, so you're going to be at the bottom, so that's a relative min. If you're at a critical point and the second derivative at C is negative, well, that means the graph is concave down and you're at the top. So if the second derivative is negative, it's concave down and you're at a place where the slope is 0, so you're at the top. Then f of C has to be a relative max. So the second derivative test says, okay, all you have to do is find the critical points. Then if it's pretty easy to take the second derivative, just take the second derivative and substitute those critical points into the second derivative. If the second derivative is positive, the graph looks like this and we've got a minimum. If the second derivative is negative at that point, the graph looks like this and we're at a max. So that's the second derivative test. We're going to do these types of things for a list of functions now. Just do a few examples. There might be another video with some other examples as well. So let's start with an easy function. It's always good to start with a polynomial function. And let's say we want to find the intervals where the graph is concave upward and the graph is concave downward. Maybe we also want to find points of inflection and talk about extrema. Okay, so if I'm trying to determine the intervals where the graph is concave upward or concave downward, first thing we always do in all of these problems is find the domain. And then after you've found the domain, then you need to find the critical points of the function. Okay, so we've got a polynomial function. So the domain is all real numbers. This is well defined all the time. Doesn't matter what x is, I can plug it in, I'll get a y value out. Now to find the critical points, remember what we're looking for. We're looking for the x values where the slope of the graph is 0, so those are potential mins and maxes, or x values where the slope of the graph or the derivative does not exist, so maybe you've got a sharp corner. It's also a potential min or potential max. We don't actually know what the graph looks like yet though, so in order to figure out what the graph looks like, we're going to compute the derivative, set it equal to 0, that'll allow us to find these points. And then we'll think about where our derivative is undefined. That will allow us to find these points. So we'll set f prime equal to 0 and solve for x. And then what else will we do? We're going to ask, are there any x in the domain? For which f prime is undefined. If there are x values in the domain for which f prime is undefined, those are critical points too. And remember, we're setting f prime equal to 0, so, or excuse me, not f prime. This is h prime. Our function is h, not f. So that's going to involve some factoring. So first thing we do is take the derivative of the first term, bring a constant down, and then you take the derivative of x to the 5th using the power rule. So you bring the power down, and multiply by x to the 1 less power. 5 minus 1 is 4. And then I've got a constant times x here. The derivative of a constant times x is just my constant. That's a polynomial function. It's always well defined, so we don't have to worry about this case. Now we just need to set h prime equal to 0 and solve for x. Now we could solve this a couple of different ways, but because we're testing intervals, well, we're going to test intervals later, it's helpful to factor it. Rather than solving this a different way, we're going to factor this. So we're setting h prime equal to 0 and solving by factoring. So first I'll factor out the 10. 10 times x to the 4th gives me the 10x to the 4th, and 10 times negative 1 gives me the negative 10. Now this is a difference of squares. Remember this fact. If you're trying to factor a squared minus b squared, it factors this way. It's a minus b times a plus b. I wrote it the other way, but same thing, right? So this is a perfect square, and that 1 is a perfect square. It's 1 squared. So I can factor that further. X to the 4th is x squared squared. So my a is x squared. X squared times x squared gives me x to the 4th. And then b is 1. So I'm adding 1 and I'm subtracting 1. Now this is also a difference of squares, so I can factor it further. X times x gives me x squared, and then b is 1, so I add 1 and I subtract 1. Okay, so I'm looking for the x values that make this 0. The only way this is 0 is if this is 0, this is 0, this is 0, or this is 0. I know some of these equations don't make sense. We're going to rule them out in just a second. But that's how products work. The only way a product is 0 is if one of the factors is 0. If all these were anything but 0, I multiply them together, I'm going to get something other than 0. But if I get 0, that means something up here has to be 0. Well, 10 is never equal to 0, so I don't have to worry about that. Now this one does not have any solutions in the real numbers. It might not be obvious to you that that's true, but it's a sum of squares, so that's one way that you can just remember that that's true. Another way that you can verify to yourself that that's true is just subtract 1 from both sides and try to solve for x. You get x squared equals negative 1. That means x equals plus or minus I, the square root of negative 1, and that's a complex number. That's a fine solution if I'm looking for complex solutions, but I'm not. I'm looking for real solutions. So that doesn't happen in the real number system, so we don't have to worry about it. Then for this term, or for this factor, excuse me, just solve for x by subtracting 1 from both sides, and solve for x by adding 1 to both sides. And those are our critical points, that one and that one. Okay, so we found the critical points. They're right there. And actually, we were not asked to find critical points. We were asked to determine the intervals where the function was concave upward or concave downward, but that's okay. I think I still want to continue analyzing this further. Let's find out where the function's increasing or decreasing. So I've got h prime. My critical points are negative 1 and 1. And h prime is the product of all these factors. It's 10 times x squared plus 1 times x plus 1 times x minus 1. And then if I want to find the sign of h prime on this interval, and this interval, and remember these are intervals of x values. X is going from negative infinity to negative 1, x is going from negative 1 to 1, and x is going from 1 to infinity. Well, I just pick an x value on the interval and I plug it into the factor, and that's going to give me the sign of the factor on that interval. Doesn't matter what x is, 10 is always positive. And it doesn't matter what x is here. If I square x and I add 1 to it, it's definitely positive. Now this one is a little different. This can change signs. So I would substitute any x value on this interval. Try negative 2. Negative 2 plus 1 is negative 1. So that's negative. pick an x value on this interval. The easiest one is 0. 0 plus 1 is 1. Choose an x value on that interval, say 2. 2 plus 1 is 3, which is positive. Okay? And then for this one, x minus 1, pick an x value on this interval, try negative 2. Negative 2 minus 1 is negative 3, which is negative. When x is 0, we get 0 minus 1, which is negative. When x is 2, 2 minus 1 is positive 1, which is positive. So I've got a positive times a positive times a negative times a negative. That makes that positive. Here I've got a positive times a positive times a positive times a negative. That makes that negative. And then the product of 4 positive numbers is positive. Now remember what this means. If h prime is positive, that means h is increasing. So h is increasing on this interval, and it's increasing on that interval. And I made it look straight, but it's not straight. It's probably curving, but it's increasing. And then on the interval from negative 1 to 1, h is decreasing. So using the first derivative test, I can see that my slope goes from positive to 0 to negative. So I'm going to have a relative max at negative 1, and goes from negative to 0 to positive, so I'll have a relative min at positive 1. So we weren't asked to do this, but we did anyway. So we'll say conduct a sign analysis. To determine the intervals where h is increasing or decreasing. And that was our sign analysis, and we've got 2 intervals where it's increasing. You always read the intervals from left to right. It's from negative infinity to 1, or excuse me, negative 1, and then 1 to infinity. And then the function is decreasing on this middle interval from negative 1 to 1. Okay, so we answered that question. And then we can use the first derivative test to classify the extrema. It's allowing us to find the relative extrema and classify them as maxes or mins. According to this chart, do the first derivative test. F of negative 1 is a relative max. F of positive 1 is a min. I keep saying F, it's H. H of negative 1, that's 2 times negative 1 to the 5th minus 10 times negative 1 plus 1 is a relative max. And so we get negative 2 plus 10 plus 1, so that's 11 minus 2 is 9. That's a relative max. And h of 1 so that's 3 minus 10 is negative 7. That's a relative min by the first derivative test. Okay, so now I know where the function's increasing or decreasing, and I know I've got a max here and a min here. Now let's answer the original question. I want to determine the intervals where the function is concave upward or concave downward. Well, to do that, we're going to make a sign chart, and we'll do a sign analysis, but for the second derivative. Pretty much the same thing. Now h prime was 10x to the 4th minus 10 before we factored. That's the version I want to start with when I'm taking the second derivative. Second derivative is just 10 times the derivative of x to the fourth. So that's 4 times x to the 1 less power. So we get 40x cubed. Now, in order to find the intervals where the function is concave upward or concave downward, we need to find out where the h double prime is 0. Those are going to create the tick marks on our number line. So when we conduct a sign analysis of h double prime, you're going to compute h double prime, set h double prime equal to 0 and solve for x. And then you also want to include x values in the domain of h that cause the second derivative to be undefined. Those need to be on your number line as well. And actually, we also need x values where the original function has asymptotes and things like that. So if the original function was undefined, those would also have to be on the number line. So we're computing the second derivative. We set h double prime equal to 0 and solve for x. Clearly, if this equals 0, that means x would have to be 0. So we've got a really simple interval, or real simple two intervals. Negative infinity to 0 and 0 to infinity. And h double prime consists of one factor, 40x cubed. Well, when x is negative, say negative 1, we get negative 1 times 40, so it's a negative number. H double prime is negative. When x is positive, so positive 1, we get 40, so that's positive. Now these two signs, you have to interpret them differently than you did up here. This was the first derivative. If the first derivative is positive, that means the function is increasing. If the second derivative is positive, that means the graph is concave upward. If the second derivative is negative, that means the graph is concave downward. And the x value, the xy pair actually, at the transition from concave downward to concave upward is the point of inflection. Okay, so we've conducted a sign analysis of h double prime. Let's answer the question that they asked. Determine the intervals where the function is concave upward or concave downward. And I'll do that on another page. So the graph of the original function h is concave upward on 0 to infinity, because that's a number line. It goes from negative infinity to infinity for x. And the original graph, the graph of the function h, is concave downward on negative infinity to 0. And 0, h of 0 is a point of inflection because it switches from, graph switches from concave downward to concave upward there. Let's say 0, h of 0, which is 0 and some number, is a point of inflection. I'll abbreviate that POI, P of I. So h of 0, well, the original function was 2 times x to the 5th minus 10 times x plus 1. Replacing x with 0, so we just get a 1. So 0, 1 is a point of inflection. Okay, what else could we ask? Someone might ask you to find the intervals where it's concave upward or concave downward. Someone might ask you to find points of inflection. Let's see. Oh yeah, the second derivative test. Now I already know the answer. I know that at x equals negative 1, we have a relative max, and at x equals positive 1, we have a relative min at those points by the first derivative test. But let's use the second derivative test to show the same thing. So the second derivative test says this. If you're conducting the second derivative test, this is what you do. First, you find the critical points. We did that earlier. We got x equals 1 and x equals -1. Then you compute the second derivative and substitute the critical points. This is actually very easy. I put f double prime, but it should be h double prime. H double prime was 40x cubed. So h double prime at x equals 1 is 40, and h double prime at x equals -1 is -40. When you're doing the second derivative test, you say, okay, well, that's going to tell me whether that critical point corresponds to a max or a min. If the second derivative is positive and we're at a critical point, so the first derivative is 0, the graph is concave up, the first derivative is 0, so we're at the bottom. So that means h of 1, which I think we calculated earlier, that was -7, is a relative min. Now, at x equals -1, the slope is 0. If the slope is 0 and the second derivative is negative, the graph is concave down and the slope is 0, so we're at the top. So that means that h of -1, which we calculated earlier, it happens to be 9, is a relative max. Now again, you do not need to do this, but that's what this tells you. If the second derivative is positive and the slope is 0, you have to be at the bottom. If the second derivative is negative, so the graph is like this, and the slope is 0, you have to be at the top. So that's just another way to determine whether extrema, or whether critical points are relative minima or relative maxima. Okay, so we found points of inflection, we found the intervals where the graph is concave upward or concave downward, and we classified our relative extrema. Let's put all these pieces together and graph H. Okay, what do we know so far? We know h of x is 2x to the 5th minus 10x plus 1. We know that when x is 0, h is 1. And we know from earlier that 0, 1, actually it's at the top of this page, 0, 1 was a point of inflection. And we also know that h of 1 equals -7, and that's a relative max, or excuse me, relative min, and h of -1 is +9, and that's a relative max. We know that the graph is increasing on the interval from -∞ to -1, and on the interval from 1 to infinity, and the graph is decreasing on the interval from -1 to 1. We know the graph is concave upward on the interval from 0 to infinity, and the graph is concave downward on the interval from -∞ to 0. I think that's enough to graph this thing. It's not going to be a perfect graph, but I can sketch a lot. I know a lot about this function just based on this. So let's plot some points. When x is 0, y is 1. When x is 1, y is -7. Okay, oops, you guys can't see that, sorry. When h when x is -1, y is 9. 3, 4, 5, 6, 7, 8, 9. Okay, so that's a relative max, that's a relative min, that's a point of inflection. And then on the interval from -infinity to -1, the function's increasing. So I don't know exactly what it looks like. I'm not really sure where it crosses the x-axis. It's increasing. Then we've got a relative min, or excuse me, a relative max. Then between -1 and 1, the function's decreasing, but from -1 to 0, we're still here. So it's decreasing and concave down. Maybe I should make a little chart for that. So all the interesting things are happening at -1, 0, +1, and then we're going to infinity. So according to this, the function is increasing over here, and it's increasing over here, and it's decreasing on this interval, and also decreasing on that interval. It's decreasing from -1 to 1. From 0 to infinity, that's over here, the graph is concave upward. So I'm using this as sort of a dividing line. And over here, the graph is concave downward. Okay, so the function was increasing from here to here, and then from -1 to 0, it's decreasing and concave downward. So it looks like this. It's a cup facing down. Now over here, it's decreasing and concave upward. So instead of like facing down like this, it's still decreasing, but it's going to face up. See how I turned it so it's facing up now? And then after x equals 1, it starts increasing again. Okay, so that's a rough sketch of our function h of x. I think it has all the properties. 0, 1 is a point of inflection. It goes from concave downward to concave upward. Cool. H of 1 is -7. That's a relative min. H of -1 is 9. It's a relative max. Good. Increasing on this interval. Decreasing from here to here. Increasing on the last one. Yep, I think it has all the properties that we talked about. So that is your example. I know we did a lot more than the original question asked, but we're basically able to put all of the information that we've studied so far together to graph this function. So you find the domain, find the critical points by setting the derivative equal to 0 and solving for x, and then we can make a sign chart and conduct a sign analysis to determine where the function is increasing or decreasing. If it switches from increasing to decreasing, you've got a max. If it switches from decreasing to increasing, you're at a min. So that's one way to find relative extrema. Now if we take the second derivative and set it to 0 and make another sign chart, we can determine where the graph is concave upward and concave downward. So you set the second derivative equal to 0, solve for x, put those numbers on the number line, and then you look at the sign of h double prime. You interpret it differently though. If h double prime is negative, the graph is concave downward. It looks like this. If h double prime is positive, the graph is concave upward. It looks like that. Any xy pair where it switches from concave upward to concave downward or vice versa, that xy pair, in this case 0, 1, is called a point of inflection. And even though this part wasn't necessary, it's a good illustration of the second derivative test. We can confirm our answer from the first derivative test by using the second derivative test. The second derivative test says you just take the critical points, which are found by taking the first derivative, setting it equal to 0, and solving for x. So the slope is 0 here. And then you evaluate the second derivative. You take the second derivative and you plug in the critical points, and that's going to tell you whether the graph is concave upward or concave downward. If you're at a critical point and the graph is concave upward, it means you're at the bottom. So the slope is 0, but the graph is concave upward, you're going to be at a relative min. Or if you're at a critical point and the graph is concave downward, well, the graph looks like this and the slope is 0, so you have to be at the top, so you're at a relative max. Now, what we just did down here sometimes confuses students. They say, how can it be decreasing in concave, or how can it be decreasing in concave upward, or how can it be increasing in concave downward? And I think you can see from this picture, or maybe let's make another picture, another couple of pictures to illustrate this. If my graph looks like this is concave upward. On this side, the slope is positive, so it's increasing in concave upward. On this side, the slopes are negative, so it's decreasing in concave upward. So you can be decreasing in concave upward at the same time, or you can be increasing in concave upward. And the same is true with concave downward. If the graph is concave downward and it looks like this, it's still possible for that curve to be curving down while the function's increasing. You're just increasing like that. Or it's possible for the function to be decreasing and the curve to be sort of curving down. So don't let this chart that we made down here trip you up. It is possible to be increasing and decreasing in concave downward, increasing and decreasing in concave upward, because you're just talking about either that side of that parabola or that side of the parabola, or that side of the parabola or that side of the parabola. You put them together and it sort of makes sense. So that's our first example, and we'll do another example or a few more examples in other videos.